Hey guys, today we're going to look at particle motion. Now, particle motions deal with particles, essentially, because particle motion, that are moving along the x or the y axis, meaning that the particle is either moving horizontally or vertically. Now, I put here that it's important to note that the position, velocity, or acceleration of a particle's motion are defined by functions, but the particle does not move along the graph of the function. It actually moves along the axis. So the actual function is just used to describe the motion of the particle, not necessarily the direction in which that it's going. So first, let's start with velocity. Now, average velocity is found by finding the slope of the secant line of the position of the function. As you can see here, average velocity, this is the equation for slope. And we use the function p of t to represent position, but it's also been used as s of t or x of t. So whatever is defined in the actual question. And whenever you see these words, right, average means slope of the secant line, and then instantaneous velocity is when it's the derivative, which could also be written as p prime or s prime or x prime of t. So that's a difference, and that's going to be for both velocity and acceleration. Average would be the slope of the secant line. Instantaneous would be the slope of the tangent line. So for this problem, it says a particle's position is given by the function p of t is equal to e raised to the t sine of t, where p of t is measured in centimeters and t is measured in seconds. And this is a calculator question, so I'm going to have my calculator out. What is the average velocity on the interval? So average velocity is going to be p of 1 minus p of 3 over 1 minus 3. So in order to get these values, we're just going to go to the calculator. Let's go to the y equals menu, and then we're going to type in this function. So e raised to the x times sine of x. And now we'll graph. Okay, so here we're just looking for the function values. I don't necessarily need to adjust my window for this or anything because the calculator is going to do all the work for us. So we can go to the second calc menu. We go to value. I need p of 1, which is 2.287, etc. So let's write this down. So 2.2873. Now we're going to get p of 3. Go back to the calculator. Now we can just click on 3, which is 2.8344. And we're going to divide that by 1 minus 3, which is negative 2. And again, I can put this in my calculator. So we're going to go back here. I'm going to exit. And I'm going to do 2.2873 minus 2.8344 divided by negative 2, which gives us 0.2735. Now it's important here that if you're given units, you want to make sure that you write down the units. P of 1 and 3 is measured in centimeters. So we just divided centimeters over seconds, since these 1 and 3 are the seconds. So my units would be 0.2735 centimeters per second. Now to get the instantaneous velocity, the instantaneous velocity is going to equal to p prime of t. So v of t is equal, v of 1.5, which is what I'm trying to solve for here. I don't like how that looks. Okay, so v of 1.5 is going to equal to p prime of 1.5. Remember that the calculator does this for us. So we can come here to the calculator. Let's go back to the graph. I'm going to go to second calc, and then I'm going to come here to option 6 for dy dx. And I'm going to plug in the value 1.5. And we get here that dy dx is 4.7874. And again, don't forget the units. So remember that the units here, because this is a rate, it's the same units as the average velocity. So centimeters per second. Now let's look at acceleration. So the average velocity is the slope of the secant line to the position function. And instantaneous velocity is the slope of the tangent line to the position function, which is what I emphasized in the previous slide. It's going to be the same thing for acceleration. Average acceleration is the slope of the secant line of the velocity function. And instantaneous acceleration is equal to the derivative of the velocity, or p double prime of t. So this is how, acceleration is essentially the second derivative of the position, or the first derivative of the velocity. So let's say that we're working with the exact same function here, the same problem. If I want to know the average acceleration on the interval 1 to 3, the average acceleration is going to equal to, let me write this out, is going to equal to v of 1 minus v of 3 over 1 minus 3. Now, this is the velocity function, and I am given the position function. So in order to find the velocity function, we need to find the derivative of the position function. So this would be a product rule question. So the derivative of e of t is e of t, and then times sine t, plus, now leave e of t alone, and the derivative of sine, which is cosine of t. So this is what I'm going to now graph on my calculator. So let's go to the y equals menu. I'm just going to deselect this graph here. And I'm going to type in my second function. So you can either type it in just as is. You can also factor out the e of t, whatever you feel most comfortable with. I'm just going to type it as is. So e to the x times sine of x plus e to the x times cosine of x. All right, let's graph. Looks very similar to the first graph. All right, I'm ready to find my function values. Remember that this is now my velocity function, so I need to find v of 1. So we go to second calc, value for 1, and we get 3.756. So 3.756. So let's write this out. So average acceleration is going to equal to 3.756 minus, now let's do v of 3, which is negative 17.0500. So we're going to add 17.0500 and divide by negative 2. Let's just go ahead and put this in the calculator. So 3.756 plus 17.0500, and then divide by negative 2, and we get negative 10.403. Now the units here, what we've just done is we've taken the velocity, which is centimeters per second, and we divided by seconds. So centimeters per second is centimeters per second squared. So that's how your units for velocity, it's always the unit of measurement over time. And then for acceleration, it's always a unit of measurement over time squared. So that's how you can kind of remember for the units for velocity and acceleration. Now, what is the instantaneous acceleration of the particle at 1.5 seconds? So that means that the instantaneous acceleration is v prime of 1.5, which is the same thing as p double prime of 1.5. That's a of t. So a of 1.5. So to find a of 1.5, what we have done here on the graph is we graphed the velocity function. So we can just simply find the derivative of the velocity at 1.5, which again, the calculator does that for us. So if I come here to the graph and I go to second calc, the dy dx, this would be the derivative of my velocity. I plug in 1.5 and I get the derivative of 0.6340. And this would be centimeters per second squared. Okay, so to kind of wrap this up in terms of particle motion, if you're given a function, I'm just going to use f of x. Okay, f of x corresponds with the position function. F prime of x corresponds with the velocity function. So the first derivative of position is velocity, and the second derivative of position is acceleration. These are the 6 main things that you need to know about particle motion. If the velocity is positive, that means the first derivative. That means that the particle is moving to the right. And that's because remember that with particle motion, it's talking about a particle moving along an axis, and usually it's the x-axis. But if in the case if it was moving along the y-axis, then that means that the particle would be moving up. If the velocity is negative, then that means that the particle is moving to the left. Now the speed is not the same as the velocity. Okay, I know that sometimes we tend to equate the two, but speed is the absolute value of the velocity. Speed is how fast the object is moving no matter which direction. So let's say if you have the velocity is equal to -1, then that means that the particle is moving to the left 1, whatever unit of measurement over time. However, the speed would be just the 1 with the unit of measurement. So the negative would just tell us the direction. So that's the difference. Velocity includes direction, speed does not. Now the speed would be increasing if the velocity and acceleration are the same signs. And the speed would be decreasing if the velocity and acceleration are opposite signs. Because if the velocity, let's say, is positive, that means that the function is moving, or the particle is moving to the right. And if the acceleration is also positive, that means that it is speeding up to the right. However, if the velocity is positive, that means that it's moving to the right. But if the acceleration is negative, that means that it's slowing down and it's going to eventually start moving to the left. Now, if the velocity is 0, but the acceleration is not, then that means that the particle is momentarily stopped and is changing directions. So that's a couple of things to keep in mind as you're working through these particle motion questions. Now let's look at an example with a graph. Use the graph of the position function to answer the following questions and justify your answer. So this is position. We can call this P of x or x of x, P of t or x of t or whatever. We usually use t instead of x for particle motion simply because it's in terms of time. Now, at which point is the velocity equal to 0? So remember that velocity is the first derivative of position. So if the velocity is equal to 0, that means that we're looking for where there's a horizontal tangent or extrema. So here we see at B and D, so we'll call this, we'll just say V of t is equal to 0 at t is equal to B and D, And the reason is because P of t has extrema. So it's the same relationship as if you're looking at first derivative, second derivative, etc. It's just now it's worded a little bit differently. For particle motion, yeah, we'll just keep going. Okay, so at which point is the acceleration equal to 0? So remember that acceleration is the second derivative. And the second derivative is equal to 0 where there's a point of inflection, because that's what that means. For our second derivative equal to 0, that means that the function must have had a point of inflection. So a of t is equal to 0 at t is equal to c. And that's because we can see here that between here to C, it's concave down, and then from C onward, it's concave up. So we would say at t is equal to C because P of t has a point of inflection. Now, on which interval is the particle's velocity positive? So remember, velocity, first derivative. When is the first derivative positive? And that's when the function is increasing. So we're looking for when the graph is increasing, which would be from 0 to b, union d to infinity. And we would say because P of t is increasing. Now, on what interval is the particle's velocity negative? Again, first derivative, negative, that means decreasing. So we would say from B to D because P of t is decreasing. Now, on what interval is the particle's acceleration positive? So acceleration, second derivative. If the second derivative is positive, that means that my function is concave up. So it's concave up from C to infinity. And we would say because P of t is concave up. Now, on what interval is the particle's acceleration negative? And this is when the function is concave down, which we can see is from negative infinity until c. So we would say negative infinity to c because P of t is concave down. Now keep in mind though, like this was just for the purposes of this question of practicing. However, because t cannot be negative, this would not exactly be valid. And some of these intervals, like for c to infinity, because as you can see on the graph that we have function behavior to the left of 0 where, you know, t should not be less than 0. But again, just for the purposes of understanding the relationship between all of this, that's why we just practiced. But keep in mind that, remember, t always has to be greater than 0. Now let's look at a sample FRQ. And this is without the calculator. Suppose the velocity of a particle is given by the function v of t is equal to t plus 2 times t plus 4 squared, for t is greater than or equal to 0, where t is measured in minutes and v of t is measured in inches per minute. For part A, we're going to find the values of v of 3 and v prime of 3. Based on these values, describe the speed of the particle at t is equal to 3. So first, let's start with the first part of this question. We're going to find v of 3. So we're just going to plug it in. So 3 plus 2 is 5, times 3 plus 4, which is 7, and 7 squared is 49. 5 times 49 is 245, and always include your units even though we're just looking for the number. This is inches per minute. Now v prime of 3, remember that's the same thing as acceleration. So what we're looking for now is a of 3. So we're going to find the derivative of v prime first. So actually I should start over here. v prime of t, which we're going to have to use the product rule. So the derivative of t plus 2 is just 1, so t plus 4 squared, plus, now we leave t plus 2 alone, and we get the derivative of t plus 4 squared, so times 2, t plus 4 times the derivative of the inside, which is just 1. So this, I mean, we don't really need to work this out or make it pretty or anything like that, because at the end, we're just looking for the number. It's actually easier to find the number if it's factored. So here, this is v prime of t, which is acceleration. So now I can plug in the 3. So now I'm just going to come back up here. So a of 3 is going to equal to 3 plus 4 squared, which is 7 squared, so 49, plus 2 times 3 plus 2, which is 5, times 3 plus 4, which is 7. So this gives me 49 plus 70, which is 119 inches per minute squared, since this is acceleration. Now, the speed, because that's what it's asking about, based on these values, describe the speed of the particle. The speed of the particle is increasing if the sign of velocity and acceleration are the same, and the speed of the particle is decreasing if the signs are opposite. Since both are positive here, it doesn't matter that they're positive. It matters that they're both the same sign, which they are. That means that the speed would be increasing. So we would say, since v of 3 and v prime of 3 are the same sign, then the speed of the particle is increasing at t is equal to 3. Now for part B, on what interval is the particle moving to the left, to the right? Show your analysis and justify your answer. So particles move to the left and right based on the sign of the velocity function. So essentially, we already are given the first derivative. We just need to find those critical numbers. And based on these factors here, my critical numbers are t is equal to -2 and -4. Now keep in mind that these critical numbers represent time. Time cannot be negative. So these critical numbers here don't really count for our derivative. So when we're testing v of t to figure out the sign, our number line would have to start at 0, since again, time cannot be negative. So we're going to plug in a value that is greater than 0 in order to see what direction my particle is going. So if I plug in, let's say 1, this would be positive, and this would be positive, so positive. So we would say the particle is always, so that way it takes care of the left situation, moving to the right for all values of t is greater than or equal to 0, or you can say from 0 to infinity, because v of t is greater than 0. Let's look at one more question, and this time it's a graph non-calculator FRQ. Okay, so the graph below represents the velocity measured in meters per second of a particle moving along the x-axis. At what values of t does the particle have no acceleration over the interval 0 to 10? And justify your answer. So no acceleration. So it's not that the acceleration is equal to 0. It's that it's when a of t is undefined. Remember that we're looking at the velocity function. So the derivative would be undefined at these values, and that's because we have a cusp. So we would say at t is equal to 1, 3, 6, and 8. And the reasoning would be because v of t has cusps. And I would also make sure to add in that a of t is undefined. For part B, for what values of t is the particle moving to the right, to the left, and justify your answer. So the particle is going to be moving to the right whenever the velocity is positive. So we would say from 0 to 2, union from 7 to 10. Because v of t is greater than 0. Sorry, I would say here particle is moving to the right. Now, the particle is moving to the left whenever the velocity is less than 0. So we're looking at below the x-axis, and that's from 2 to 7. And we would say because v of t is less than 0. Express the acceleration a of t as a piecewise function defined function on the interval 0 to 10. So a of t is the derivative of v of t. These are all linear. So the derivative of v of t is the slope of each of these lines. So we would say that a of t, the slope here is 3. So we would say 3 for the interval 0 to 1. So we go 0 less than t less than 1. And I'm not including these values because notice that it's the open interval. Now over here, the slope is -3. And this is on the interval 1 to 3. So 1 is less than t is less than 3. From 3 to 6, it's a horizontal line, so the slope is 0. For 3 is less than t is less than 6. Over here, my slope is 3 again, and that's on the interval 6 to 8. So 6 less than t less than 8. And on this last section here, my slope is -3 over 2. So, and that's on the interval from 8 is less than t is less than 10. Now it says to find the average acceleration of the particle on the interval 1 to 8, show your work, and indicate units of measure. So average acceleration, remember, is the slope of the secant line. So that's going to equal to v of 1 minus v of 8 over 1 minus 8. V of 1 is 3 minus v of 8 is 3 over 1 minus 8, which is -7. Now this is just 0 divided by -7. So my average acceleration for that section would be 0. And then even though it's 0, we still want to include the units, which is meters per second squared. And that's particle motion.